So welcome to the session where we are going to talk about paging. Paging, as I had mentioned in the lecture, previous lectures, is one of the most interesting architectural innovation. This allows a programmer to have a view of a 4 gigabyte if it is in the case of a 32-bit architecture, but execute a program as large as 4 gigabytes in a very small memory. And the reason for that is the statement that I made: for me to successfully execute a program and take it to completion, it is enough if at every point of time the next instruction to be executed and the data required by the next instruction to go to completion, if these two are available in the RAM, the random access memory, it is sufficient for us to complete the program. And this is what we started, and from that evolved the concept of paging. And in the sessions we did talk about paging and how it is enabled specifically in the x86 platform in detail. Now we will see a lab which will basically talk about all the things that an operating system needs to do to enable paging. And once that is done, then we will also go into subsequent ways by which you can demonstrate paging. So these are all some of the steps, as you see on the left hand side in your screen, some of these steps taken by the operating system. First thing is, it needs to set up all the control registers for enabling paging. Specifically, we will now talk about 4 KB pages, which is in hexadecimal it is 0x1000. We will set up the page directory at 0xe1000. So let me just recall, till about A1000 it is all the GDB kernel in your guest machine, and then from A1000 to C1000 it is going to be A1000 to C1000, A1000 to D1000 DFFF. It is going to be some pages of code and data, and from E1000 we have some available space. So we will set up the page directory in the page 0xe1000 to 0xEFFF, and then a page table starting from 0xF1000 to 0xFFFF. Right. So, and we will do the following: the page containing the code, that is 0xa1000 to 0xAFF, will be identically mapped. Similarly, the page containing control data, namely the GDT, IDT, LLDT, will also be identically mapped. And the page containing the page directory itself, which is 0xe1000 to FF, it should also be identically mapped. And the page containing the page table, that is 0xF1000 to 0xFFF, that's also to be identically mapped. And what we do is, all the other even pages we map it to 0xB1000, and all the odd pages we map it to 0xC1000. So the entire setup is, I have one page directory, all the entries in the page directory will point to a same page table. All the entries in the page directory will point to the same page table. What is that page table? Which is be pointing from 0xF1000 to 0xFFFF. And every entry in that page table, all the even pages will be mapped down to 0xB1000, all the odd pages will be mapped down to 0xC1000, except those pages which contain the code, which will be identically mapped, the page which contains the control data, that is 0xC1000 to 0xCFF, that will also be identically mapped. And then we will have the pages having the page directory and the page table themselves, they will also be identically mapped. Why they need to be identically mapped is already explained during the part of the lecture. For example, if the code, the page containing the code, if it is not identically mapped, namely 0x8000 to 0xAFF, which actually enables paging, then what happens is, the moment you enable paging, then the next instruction to be executed will be translated and it will go to some other page. So it is very, very important that we map that 0x8000 to 0xAFF. That is the page which is enabling paging onto itself, so that once you enable paging somewhere in that page, the next instruction to be executed will also belong to the next instruction in that page itself. So this is very important. We have already demonstrated in the class. Now, after doing all these things, after establishing this page directory, this will be completely done by the operating system. So when your program is going to be loaded, all these things would be set up. Then what you do in the program is to demonstrate how paging works. So you actually access very large addresses. For example, you go and write into a very large address, but that will be into a page, either B1000 page or the C1000 page. So you'll write into one of those two data pages. Similarly, you will jump to a very large address, but that will be the next instruction. So these things will basically demonstrate how paging works. The next thing that we would like to also tell you is that we will also create a page fault. That is, we will go and make one of the entries as the page not present, and that will create a page fault. And then we will take you to a interrupt service routine which is handling that page fault. Essentially, that will be the page fault handler in the operating system. So, and what it will do is that in practice, it has to go look for the page in the disk, load it here, and if needed, it has to do a page replacement policy. So many things it has to do, and those things would be covered in an operating system course. And after doing all these things, it will make the page as present and then return back the control. So what this ISR routine will do is to actually go and make that page as present, and it will allow you to continue, right? So essentially, by doing this, we know how a page fault occurs and how do you transfer control to a page fault handler, and then mimic some functionality of the page fault handler and return back and start executing them. And finally, we will go and disable paging before we come out of the program. So this is what we do as a part of this complete programming assignment. Right? Now we will go into the code. So this is the host machine. The other machine is already running. The guest machine is already running. Now we are in lab. We have to go to lab 3. And you have this everything here. So what we do is /gdb comma lab 3. It's compiled now. Now we will go and do a new tab.
Inside this,
We'll create a new tab here. So we are gone here. So we'll now go and say so these are the typical commands. Now we have come to this stage. Now we will go and load lab3.out. We'll again load lab3.out, and now we'll go and see where all the pages are loaded. First and foremost, let us go and see where is x slash, say, some 10x of 0x e1000. So all the entries in e1000, as you see, points to f1000. Right. So this is how the page directory entry. Please note that the last 12 bits are used for privilege and other things. So please note here that all the entries are pointing to f1000, right? And there will be one entry in which the thing is not present, the page not present, because we wanted to create the page fault. And that entry is so let us go and see. So we are seeing the code here. So that is, I have made it as x slash 2x or even x slash x. Let us go and see 0x EEFFC. And so this is now pointing to f1000 entry. So inside f1000 entry, let me go and see 0x ff. Let us see what is there in f1000. So x slash 10x. Now note that pages are pointing to b1000, c1000, all the even pages. That is, page number 0 is pointing to b1000, page number 1 is pointing to c1000, and so on. Right? Now let us go and see one page where I want to create a page fault. Please note that 17 essentially means that page is present. All these pages are present. Now let us go and see x slash x 0x FFF8. Yeah, this is alone B016. So just to make it a little more, this thing. Okay. So as you see that this is alone B016 or S less than FFF0. This is all B017, C017, but this is alone B016. So that page alone is not present. We will use this particular entry to create a page fault, which is there in FFF8, right? So if you look at the code on your right hand side, you see that that has been given here. So I am generating some huge address which will map on to this FFF8, right? And there you find out that the page is not present. Okay. So this is basically how I generate an fault. Now I have to also tell you that some of these pages are identically mapped. So let us go and say, where is A1000 to be mapped here? Which entry would be A1000? Right? So let us go and find out which entry A1000 will be. So let us go and see where. So I just leave it as a 1 minute exercise for each one of you. Where will A1000 be mapped? So that the first entry would be all zeros, because the first 10 bits are 0. If I take the address 0x8000, the first 10 bits are all zeros. So that means So I now go, the first thing is I go to E1000, I use the first entry there, the 0th entry. The 0th entry now points to F1000. Now in this F1000 I have to index with A. What is A? A in hexadecimal is 10. And so each entry is 4 bytes, so I have to go 40 bytes into this. What is 40? 40 is 28. 28 is 2 into 16 is 32 plus 18. Hexadecimal it is 28. So I'm going into the page directory, page table, which is at F1000, and going to the 28th entry. And note that the 28th entry is now A1017. It is mapped, identically mapped. Okay. Now just see that we'll just do some 10 to just show you how it is going to work. We'll just see x/10x. Now you see that B1000 is mapped down to B1000, C1000, etc. The odd and even page. Now this is the 28th entry. It is mapped down to itself. And please note that the next page B1000 is mapped down to itself here. And then the next page C1000 is mapped down to itself. Now you also see that the D1000 page is mapped down to itself. This is the control page. Then E1000 is mapped down to itself. Then F1000 is mapped down to itself. And again you start doing B1000 and C1000. So the mapping is pretty clear here. Right? So now we will now go and start analyzing this code that you see on the right hand side. So what you see here till this we have already seen, and please note that at this point of time I have my all my DS, SS, ES, FS, GS pointing to 0x10, which is one, and my code segment is at 0x8. So let us start having a workspace here. So now I am in line number 46. When I reach line number 46, your DS, FS, ES, GS, SS all are pointing to 0x10 selector. Your GDT is already there in D1000. So let me go and see x/2x 0x D1000 and sorry, it's 0x10 D1010, and so this is B1000. So here the base is B1000 for this, and limit is 0x BFF. That means 0x B1000 plus 0x BFF. It's a large limit that you have put here. And your code segment is pointing to 0x8. So let us go and see what is there in 0x8, D008. This is the GDT. So this is a code segment. This is of privilege 0. So base is 8000, and limit is FF, very large limit, and then privilege level is 0, as you see here. You can just go and interpret. I hope by now you are all very clear with segmentation. So this basically gives you that privilege level, right? And here also the privilege level is 0 for all. Okay, so this is basically where we are when you come here, and your stack pointer currently is at 1FF0, right? Now what we do here? Now let us go and start doing this code. Now I am coming here. I am moving move AX comma 0x18 to DS. What is 0x18? So x/2x D018, and that starts with B1000 and a limit of 2000, and it's again privilege 0. Okay. So now at line number 87, we have now made ds point to 0x18, and that has now limit, sorry, base b1000, limit is only 2000, and privilege level is 0. And these are the things that we are, and it's of type 2, so it's a read write segment. Then now GS, we have made it as 0x30. GS we have made it as 0x in line number 91. So in line 91, I am making GS as 0x30. That essentially means x slash 2x 0x 0x d0 30. Now this is a segment with base as 0 and limit as FFFF 5Fs. Limit as 5F, and so this essentially and also the granularity bit is set to 1. So this can essentially cover PL is 0, and it's please note that the granularity bit is also set to 1. So this can cover 4 GB. Interestingly, also see that if I just see the mouse here, if you take the code segment, again there also the granularity bit here is set to 1. So the limit is interpreted as 4 KB. So even here this is a 4 GB page. So base, from base I can go as long as base plus 4 GB, right, meaning it will wind up, and here base plus 4 GB, we can go up to 4 GB here. So these are the two code, and now I make the stack point to 28. So this is line number 95. As you see here, I make the stack point to 28. So line 95, I make the stack pointing to 28. So that means its base is, let us go and see here, its base is CF100, its limit is 100, and its privilege level is of course 0, and it's just a normal page. It is not a magnified page. The granularity bit, as you see here, this 4 basically indicates that your granularity bit is 0. So this limit is interpreted as 100. Note that the stack is in a page which is identically mapped, because C is mapped identically onto itself. Okay, so this is also very important. Now let us go to the next line. So now we also set ESP as 0x100. So ESP now points to the limit of the stack. So when I am pushing, it is a growing down stack, so it will start working correctly.